Hello, I welcome you all to this another interesting screencast where we are going to be solving this engineering mechanics problem, and it reads determine the moment of inertia of the beam's cross-sectional area about the centroidal y, x and the y axis. This problem is coming from the engineering mechanics statics textbook 13th edition by R.C. Hibbeler. Right. So moment of inertia of an area is also called area moment of inertia. It is also called second moment of area, and this is a geometric property of an area or a shape, such as a cross-section of a beam, which describes how and the area is distributed around an axis where we want to find moment of inertia of an area. Mathematically, it is described as moment of inertia about the x-axis is I sub x, which is equal to integral of y squared dA. Moment of inertia about the x-axis is defined as y sub y integral of x squared dA. So we are going to use the parallel axis theorem for this particular problem, which is just simply defined as moment of inertia about the x-axis is equal to I sub x is equal to I sub xc, which is centroidal moment of inertia about the x-axis, plus dy squared times area. This dy is the distance from the centroid of each particular area or part to the axis where we want to find our area moment of inertia. The moment of inertia about the y-axis using the parallel axis theorem is equal to I sub y equal to y centroidal moment of inertia about the y-axis plus dx squared times area. Our dx in this case, dx is also going to be defined as our x curled, okay, and dy will be defined as our y curled. Alright, so what we need to do is now to label the parts. Okay, so let me label the parts so that I start working on them individually. So I will have the first part. Let me call this one, and when you look at this particular composite shape, is symmetrical. The ones in red are symmetrical, both about the x and the y axis, therefore they will have the same part number. And the one in blue, the one I'm labeling in blue right now, are also symmetrical about both the y and x axis. Let me thicken it a little bit for this one. So they will have the same part number 2. Okay, so there we go, something like that. Okay, so let me call this as my part 1. As my part 1, this is both 1 and then this is both 2. Okay, so ideally we only have 2 parts. So let's find moment of inertia for each one of those. Centroidal moment of inertia, I'll just find for 1 and then multiply it by 2 because of symmetry. So moment of inertia centroidal, we are dealing with centroid right now. So this is centroidal, local centroidal, moment of inertia. So let's start with about the x-axis. So for part 1, I'll just say x1, and there are 2 of them. I'll just say 2 because of symmetry. Then 2 by bh cubed divided by 12. So this is equal to 2. Our b for part 1 is 300, and our height is just 30 to the power 3 divided by 4. So let's find out what this gives us. 2 by 300 by 30 to the power 3 divided by 12. So this we have 1.35 and 10 to the power 6. Then moment of inertia for part 2. Also there is symmetry, so multiply them by 2. BH, multiply them by 2. 2 BH cubed divided by 4. Okay, divided by 12. So this is equal to 2. Our B for part 2 is 30, and then our H is 200 to the power 3 divided by 12. So this gives us, that's 2 by 30 by 200 cubed divided by 12. This gives us a 40 times 10 to the power 6. Great. And then moment of inertia about the y-axis, centroidal. For part 1, again there are 2. This is a rectangle BH cubed divided by 12. So we have 2 by, what's our B? With respect to the y-axis, our B is 30. Okay, and our H is 300. Okay, 300 to the power 3. 300 to the power 3 divided by 12. So let's say what this gives us is 2 by 30 by 300 cubed divided by 12. So this gives us a 135 10 to the power 6. So huge, right? 2 by 30 by 300 cubed divided by 12. Yeah, okay. And then for part 2, IY2 equal to, there are 2 of them because of symmetry, BH cubed divided by 12. So it's 2 by B. What is B for part 2 is a 200. And then what is H? H is a 30 to the power 3 divided by 12. So we have a 2 by 200 by 30 cubed divided by 12. So this becomes a 0.9 10 to the power 6. Great. And then what else? Let's find the area. So area 1, again there are 2 areas, so just say 2 LB, 2 by LB, which is just equal to 2 times, what is our L is 300, and what is our B, it is 30. So here we have 2 by 300 by 30. So this becomes 18 10 to the power 3. And then area 2, there are 2 of them. with they're similar. So 2LB, which is equal to 2 times 30 by 200. Okay, so it's 2 by 30 by 200. So this gives us a 12, 10 to the power 3. Let's define the centroidal for part 2. So for part 2, centroidal for part 2, let's say this is the center. Okay, let's say somewhere there. Okay, like so. And then let me extend it down there. I also put like so there. I draw like so, and then let me put another color here. Okay, maybe I extend it down there like so also. Okay, something like that. Alright, so there we go. Just try to make it better. So something like that. Right, so there we go. So this one here, this one here, this one we are going to call it as our y curled 1, okay, which is equal to this is equal to half of 200, which is 100, then minus half of 30. Okay, and therefore this gives us a what? That minus this gives us 85. So this is the same value also here, 1 curled 1, and then this one here, is equal to, this one is so this is y1, and then this one is going to be equal to x curled 2 is equal to 150 plus half of 30. This is going to be equal to 150 plus half of 30. So this gives us 165, and this is again x curled 2. Okay, and then the other values, y curled 2 becomes equal to 0, right? 0 for because yes, the rest becomes 0. Okay, so we know that y curled 2. Okay, so if this is the distance, then y curled 2 is equal to x curled 1 for this one, y curled 1 which is equal to 0. Okay, so let's fill in the table quickly. So we have part, then we have centroidal, moment of inertia for each individual part. Then we have y curled, then we have area, then we have y curled square times area. Then down there we have part, y centroidal, x curled area, and then x curled square times area. So 1, 2, summation, 1, 2, summation. So let's fill in the table. We have moment of inertia for part 1 about the x-axis centroidal is 1.35 10 to the power 6. The second one, of course, we had to multiply by 2. It's a 40 10 to the power 6. Okay, and then the total, if we are to sum up this just gives us a 41.35 10 to the power 6. Centroidal distances along the y direction for y1, we said this is 85. It's 85. And for of course it's 85. And then we have for YQ2 is 0. Okay, YQ2 is 0. And then for area, we said area 1 by 2 is 18 10 to the power 3. Area 2 by 2 is 12 10 to the power 3. Then the product of the two, 85 squared times 18. 85 squared times 18, this gives me a 130.05 10 to the power 6. So 85 squared by 18. Then this one is just a 0, and the total there is just 130.05 10 to the power 6. Okay, so let's find the total there. Moment of inertia is going to be equal to the local centroidal plus y curled squared times area, which is equal to 41.35 10 to the power 6 plus 130.05 times 10 to the power 6. Therefore, moment of inertia about the x-axis becomes as 41.35 plus 130.05. So this gives us a 171.40 times 10 to the power 6 or millimeters to the power 4. So let's go to the second one. Moment of inertia centroid about the y-axis. For part 1 we have 135 10 to the power 6. For the second one we have a 0.1 second part 10 to the power 6, and then x scaled 1 is a 0 for part 1. X scaled 2, it is a 165. Okay, it's a 165, right? That's a 150, then half of 15. Half of 30. Then area does not change, it maintains 18 10 to the power 3 and the 12 10 to the power 3. Of course we have here the product is 0, and then we have this other one here which is 1 65 squared by 12 gives us a 326, a 326.7, 326.7 10 to the power 6. Alright, then we sum up this. This gives us a 135.9 10 to the power 6. We sum up this side is just a 326.7 10 to the power 6. Then finally, we have moment of inertia about the y-axis, which is equal to centroidal moment of inertia about the y-axis plus x scaled squared area, which is equal to 135.09 10 to the power 6 plus 326.7 10 to the power 6. Therefore, moment of inertia about the y-axis is equal to 135.9. This is 135.9. Okay, let me write this. This is 135.9 10 to the power 6 plus. So moment of inertia I sub y is equal to 135 plus 326.7. This gives us a 462.6 10 to the power 6 millimeters to the power 4. Okay, so we have the moment of inertia about the x-axis. We have the moment of inertia about the y-axis. Alright, I think this is about it. This is one way of solving this. Of course, if you had wanted to, you could have used the other way where you just calculate the whole area and then you subtract the inside area, which is this one. Okay, this is another method of doing it. Okay, it's up to you, whatever comes in your mind first, then you can choose whichever method works better for you. Right, so moment of inertia about the x-axis 171.4 10 to the power 6, and moment of inertia about the y-axis is equal to 462.6 10 to the power 6. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.